Okay, hello everyone. Welcome to my power system analysis videos. And today we are presenting a class about direct current transmission systems. As you must be aware, this is the third video related with DC transmission. Okay. Okay, let's go for business. If you are watching this video, I assume that you already are you already subscribed to my YouTube channel. Over here there is a link. Also, if you want to get more information, please go and download the slide to my ResearchGate or some numerical examples at GitHub. Okay. If you want to follow me on Twitter or LinkedIn, that could be helpful. Okay. Well, let's go for business. What is the topic today? The topic today is I will start with a short introduction. Sorry, about direct current transmission systems, and then I will go to talk specifically to line commutate converters or current source converters, and I will go in details into the rectification and inversion. Okay, converting from AC to DC and from DC to AC. Okay, basically that is the thing. And then I will talk about a very short description about controls at LCC or current source converters link. Then I will talk about how the what is the structure of what typically is the structure of a HVDC transmission system. Then I will go for a voltage source converter, short explanation about the beautiful controllers over there, active power and reactive power. Then there is a short summary, and finally a couple of references. Okay, this presentation over here is basically based on the book of WD and Starbuck Electrical Power System Analysis from Wiley. Okay, let's start with a very short introduction about transmission system. I believe all my students are aware that AC has been dominant on the transmission system for many years, and three-phase AC systems, they are dominant for transmission. Okay, however, there is a limit on the distance that you can transport massive bulk power. Okay, and that limit is related with voltage problems. Okay, if you start to use some form of reactive power compensation, of course you can extend the limit, but you must understand that there is a cost related with the reactive power compensation. Okay, for that reason, typically we try to use these short transmission lines, or if we are using long transmission lines, they are some chunk or series compensation. Okay, for long distances, it's been a clear situation where HVDC is dominant. Okay, however, the recent development on offshore wind power and also for the deep sea offshore wind power, that made possible that we can explore the wind resource very deep in the North Sea, for instance, and that means that far away from the coast we need to use undersea cables, and those undersea cables they require a lot of reactive power, a lot of capacitive charging on AC cables. And that is one of the reasons that recently we start to use voltage source converters and HVDC system for undersea cables. Okay, distances undersea cables with distances larger than 50 kilometers. That is the point that we need to start to use submarine or undersea cables. Okay, here I am presenting a comparison, cost comparison between AC and DC. Okay, As you can see in blue color over here, we have the line representing the blue line represents the DC systems and the red line represents the AC systems, okay? And here we have the cost related with the AC station, okay? As you can see from this distance to around 800 kilometers using overhead transmission lines, the cost of using AC solutions are cheaper than the cost of using DC solutions, okay? Then there is a point that is the break even distance, and from that distance on the situation change, and AC systems start to be expensive compared with the blue one that represent the DC systems, okay? Something that is important is that you must understand that typically the break even distance, if you are using overhead transmission lines, is around 800 kilometers, and that is the reason that we use AC lines for those short distances, okay? However, if we are working with undersea cable submarine circuits, 50 kilometer is the break-even distance, okay? If you need to install a offshore wind farm and this is located beyond 50 kilometers, the optimal economical solution is using HVDC, okay? There are many use of interconnectors around the world. And for instance, I can tell you that the UK or the GB system and France, they have several interconnectors. One of them is the UK-France cross-channel link that is around 2000 megawatts, okay? Another application, I already say to you that another application is the interconnection of systems with different frequency. If we have a system operating at 60, another one working on 50, the only solution to interconnect or make a connection between those systems is using the DC link, okay? That is the case that I already explained to you in several videos before, and that is the case between Brazil and Argentina, Brazil and Uruguay, Brazil and Paraguay, okay? But I forgot to say that also in Japan, okay? You must be aware that Japan is quite interesting because between the North and the South Island in Japan, they use 50 and 60 hertz, okay? On the other hand, DC transmission lines has been used, overhead transmission line has been used for very long distances and for very long distances and for transmitting very high power, okay? That is the case, for instance, of the Nelson River scheme in Manitoba with 4,000 megawatts transmission, okay? And now let me show you here what is the typical classification of what is the most commonly used converters for HVDC, okay? Well, there are typically two types of converters, one that we call current source converters, and they use basically, those converters use thyristors that they are triggered by a gate pulse, okay, and they turn on when the current fall down and the voltage is also crossing zero, okay? That is basically the fundamental for the current source converters. They use thyristors, and when there is a zero crossing, they switch off, okay? And on the other hand, they can be modeled like current sources, and as you can see over here in this representation, the idea is that we have a current source that is providing the DC current into the system, okay? On the other hand, one of the problem of this kind of DC system is basically a lot of harmonics pollution on the AC side and the need for filters, AC side and DC side, okay? On the other hand, we have here the voltage source converters. The voltage source converter, they are designed to operate with what we call self-commutating devices that we can switch on and switch off depending on a signal at the gate. And that is the case that we use the insulate gate bipolar transistor, or IGBT, or the GTO Okay, the voltage source converters, they use this kind of devices that they can be turned on and turned off basically depending on the gate voltage. Okay, those converters they are also called force commutate converters. Okay, they can operate in any combination of active or reactive power. They have the ability of operating in a quick grid, and also have the functionalities for black start. Okay, black start is a very important functionality. If you have a blackout and you would like to restore your system, those voltage source converters, they can be used to provide voltages and restart or restore the system. Okay, also those voltage source converters, the IGBT and the GTO, they have very fast acting response, and as consequence we can use very fast acting controllers, and we can have a precise control of the electrical variables. Okay, many techniques has been designed for the operation of or switching or commutation of those devices. Okay, but typically we can use some sort of PWM, that is a technique that allow very low harmonic distortion. Okay, however, one of the disadvantages between the voltage source converter and the current source converter is that they still smaller in terms of capacity. Okay, they are very the rating is very much lower than the current source converter. Okay, the thyristors has been a technology for many years in the market. They are in a very big very high power and high voltage, and as consequence they are still dominant in that sense. However, voltage source converters, IGBT, the technology is increasing quite fast, and we are going in the increasing power over there. However, one of the issues of the voltage source converter, and still a disadvantages, is that they have a sensible, a bit higher active power losses compared with the classical LCC or current source converter. That is coming from the switching that we have at the device. Okay, and now let me talk about switching devices. Okay, I think I explained a bit about those thyristors, but what you need to understand is that those switching devices, they are created using some semiconductor material. Okay, as you can see over here on the left hand side, they are PN configuration. They are basically 4 layers of different semiconductor materials, and that create the structure. Okay, and what is interesting over here in the middle, we have the circuit representation. You can recognize there is an anode, a cathode, and a gate. And typically when we apply a positive pulse here at the gate and the letter G over there, then the conduction starts. Okay, what I trying to say is that when you apply here a positive pulse at the gate, we have a conduction between A and K. Okay, however, there is a problem, because after we switch on the device, we need to wait until the current fall down, and the voltage because the voltage is changing also, and when the current is reduced, the device is reset and open. Okay, what I'm trying to say is those devices, we can have control where to switch or when to switch off the device. However, when the conduction is started, there is no more control until there is a change on the current. Okay, and basically those devices receive the name line commutate devices, because in order to stop the conduction, you need that the line change the current going to 0 or reduce until some level. Okay, as you can see over here at the far right, you can see the characteristic. If you are a power electronic person, you will realize that there are some small voltage during the conduction, and that small voltage is basically the voltage drop across these unions here between the material P and N. Okay, if we keep going here, the modern technology has increased the development of those thyristors, and right now there is a possibility that the gate will be excited using light, okay? And that is the reason that modern thyristors, they are using, instead of pulse of current, they are using basically some light pulse that is sent by using optic fiber, okay? And this fiber optic channel is basically the pulse that is commutating the device and starting the conduction, okay? However, something that is important is to increase voltages and increase currents. We need to use series and parallel configuration of those thyristors, okay? And something that we need to be aware is that we need several additional elements, circuit elements, in order to obtain a uniform voltage distribution across the thyristor, and also to be careful about the rise of the current, okay? The IDT and the VDT across those devices, electronic devices, they are very, very dangerous, okay? On the other hand, this is the famous IGBT, insulate gate bipolar transistor. They are very beautiful and used to create the voltage source converters, okay? In those devices, in those commutation devices, the IGBT, they are basically a step forward on the MOSFET, okay? Coming from the analog electronics, they are an evolution of the MOSFET, and basically we have here a structure that you have here, PNP materials, okay? It's very similar in terms of construction, I mean, in terms of the number of material, but the construction, the geometry is a bit different, and that is what creates the basic properties of this device, okay? In this device, again, we have three different terminals. Names are different. This is the collector, this is the emitter, and this is the gate, okay? When we apply, when we remove the voltage from the gate, the device is switched off. When we apply here some voltage between the gate and the emitter, we have some conduction, okay? Over here on the far right, you can see the classical current voltage characteristic. This is the voltage characteristic across the terminals, collector and emitter. And here you can see the amount of current that is flowing when there is conduction. Over here, you can see that increasing the voltage between the gate and the emitter, you can have more conduction across the device. Okay. Okay, this device is typically a very efficient device in terms of starting and stopping the conduction. However, you must be aware that during the conduction, this device has a very low voltage, okay? And that is typical in any electronic device. It's around 0.7 volts coming from the PN union, okay? However, those devices are still a bit expensive compared with the classical thyristor for the same power and the same voltage, okay? Now it's time to move for the next topic. And let's talk about current source converters, okay? Let's start with the old technology, the technology based on thyristors, the technology that is dedicated as high power, high voltage, but is represented by a current source, okay? If you look over here, I am presenting two different HVDC systems using thyristors. However, one of the issues related with the HVDC as a current source converter is that changing the power flow direction is a very complicated situation, okay? And why is that, okay? Basically, the problem is coming that in order to change the power direction, we need to change the polarity of the sources, okay? What I'm trying to say is if we are sending power from 1 to 2, the converter at the left-hand side must be the rectifier, and the converter working on the left-hand side, feeding power into the system number 2 must be working as inverter mode, okay? And to do so, the voltage VDR should be larger than the VDI, and the current will flow from the left to the right, okay? However, if you look over here down, the power flow direction is changed, okay? If you look over there, again, we have here the current moving from the left to the right, okay? However, as you can see, the voltage polarity has changed, and right now the converter station on the right hand side at the system number 2 is working as rectifier, and on the other hand, the converter connected to the system 1 at the left hand side now is working as inverter, okay? Conclusion from here, and when we are using current source converters, when we are using LCC, one of the issues is changing the power direction, okay? Because you need to change the polarity of the converter station, and that means also changing the operating mode, okay? And that is something that is not so easy in this kind of technology. And I almost forgot that also changing the current direction, and changing the power flow direction is also affecting the cables, okay? It's something good that you can read about the technologies used for HVDC cables, and you must realize that also that is affecting, okay? For now, what I will do is I will start to talk about the 2 different operating modes, okay? I say that we have something that is called power electronic converters. Those power electronic converters, they use some thyristors in order to perform commutation, okay? However, depending of the operating regime, we can have rectification or we can have inversion. What is basically the difference? Well, in rectification, we have AC signals, and we are converting those AC signals into direct current, okay? AC coming in and DC coming out, okay? Over here in this plot, what you can see over here is we have here a rectifier, okay? As you can see over there, we have a 3-phase rectifier, and in these 3-phase rectifiers, at this moment, we are not inserting any signal to the gates. That is what we call there is no gate control, okay? If there is no gate control, those devices will conduct and will allow the current to move through is when the device reach a terminal voltage that allow the conduction, okay? If you look over here, I am representing in blue color the total sine wave that is present inside the 3-phase rectifier, okay? There are 3 blue signals over there representing the 3 different AC signals, okay? However, you can see that there is a very changing wave that is in black color, and that represents the voltage that is obtained basically on the rectification on natural operating mode of this rectifier, okay? That is the classical shape. As you can see over here, the average value of those blue signals is 0. However, when you start to use this rectification process, we have an average or mean value of this direct output, okay? Over here, you have all the mathematics. You can do the calculations, and I put over there the angles. However, what I need that you understand is that the rectifying process is taking the maximum instantaneous value of the signal or the peak value of the AC signal, and is adding some multiplier, in this case 3 square root 3 divided by 2 pi, in order to define what is the mean average value or the mean value of the direct output voltage, okay? In this case, again, I am telling you, this is a situation where there is no signal going into the gate, and this is the natural process of rectification, okay? That situation is a bit different if we are in some other situation. Okay, let me imagine now that we have right now some commutation time, okay, or some overlapping angle. Okay, what does mean the overlapping angle, or what does mean the commutation time? Okay, what I'm telling you now is that you are sending some signals to the gates of those devices, and now you are starting the conduction. And in this case, you are performing intentionally the conduction of those devices. Okay, and from where, what I want that you understand is that we have the blue signal again, that is the supply voltage, and over here you can see the commutation angle, or the commutation time. Okay, in this case, what is important that you understand is that when we have the commutation and there is some inductive component inside the device, now the current cannot be a step. Because if we have some inductive component inside the circuit, the current cannot move instantaneously from 0 to the full current. In that case, we have some transient, and in that case, the current will take some time going from the maximum value to 0, okay? And that is affecting because there are some voltage drop that is created during that process, and that is the reason that this plot in black color is different to the previous one that was totally matching the intersecting point between the signals. Okay. However, what is the important conclusion here? I don't know if you realize, but this small transient over there related with the current that is affecting the voltage, that is related with the commutation time or the overlapping time. Okay. However, what is the interesting thing here? Well, that you can imagine this gate, this no gate control, like gamma equals 0. What I'm telling you is, if this angle here or this delay is 0, well, you will have the same signal that we got over here. What you need to understand is that when we have some commutation and there is an overlapping, if that overlapping is 0, that represents the natural and ideal representation of the three-phase rectifier, okay? And now what I am doing is, okay, now let's have some gate control, and right now we have a delay angle alpha, and now we have the commutation angle gamma, okay? The commutation, the delay angle or commutation angle is basically the position where the thyristor starts the conduction, and as you can see, gamma is coming from the previous slide, is basically the commutation angle, and that is related with the process of the transient between current and voltage, okay? What is important that you understand now is that in this case, the direct output voltage is modified, is still 3 square root 3 over 2 pi, but now we can include the angle based on the previous equation, and we can define what is the effect of the angle alpha into the direct output voltage, okay? What I'm telling you is this is the value if we don't have any alpha, any gate control. But if we insert the gate control, we are multiplying by the cosine of alpha, and that is the effect, okay? As you can see over there, if alpha is equal 0, well, we keep having the original value that we have, but instead of increasing alpha, well, V0 start to decrease, okay? And now, what I want to show you is, what is the situation if we start to think about three-phase systems, okay? Right now, we have over there a bridge arrangement of commutation devices, okay? There is a voltage supply. You can see VA, VB, VC in blue, black, and green color over there, and that is the voltage that is coming from the transformer, okay? Then we have here several arrows in red color, I1, I2, I3, R4, R6. those currents are the currents moving through the commutation device. For instance, the first plot over here represents the current going through to the first switching device, Q1 or 1, okay? As you can see over here, the current is going from 0 to 1 value, then going back to 0, and then when the device commutate again, when the device commutate again, well, we have another step here in current, okay? However, you must realize that there are two devices in series, two commutation devices in series for each phase, okay? And in this case, the total current on A, I mean the total current here in A, is the relationship between the current on the commutation device 1 and the current commutation going from the device number 4. What I'm telling you here is that now, using this very intelligent commutation, we are transforming those currents that all of them are positive, and the current that is moving through this phase A is basically a current that has steps, positive and negative steps, okay? And what is the interesting thing, okay? Starting from this real representation of the bridge converter, okay, of the bridge arrangement of switching devices, we can come here to a simplify or modify version, okay? However, what is the important part that I need for my students think about now, okay? What I need now is that my students understand that when we are working with three-phase systems, we are using line-to-line voltage. And now the mean DC voltage of the bridge rectifier is V0. And V0 right now will be 3 times the square root 2 divided by pi multiplied by the line-to-line voltage, okay? What I'm telling you is the DC voltage of this rectifier is related with the line-to-line voltage. You can use, I prefer that my students use the proper equation, 3 times the square root 2 divided by pi, but if you are a bit, if you prefer just numbers, 1.35 do the job, okay? Again, we can compare when we have when we have the angle alpha, when we have the angle alpha and gate control, where the cosine of that angle is modifying the maximum value that we can reach, 3 times the square root 2 divided by pi line-to-line voltage, okay? Here is the full sequence. Here is the full sequence when we have the full bridge. And over there, I am representing all the signals for the commutation of the device 1, 2, 3, 5. 1, 2, 3, 4, 5, 6. And also below, you can see the currents that they are coming from this rectification process, okay? And over there, what I am doing is, okay, if we want to obtain the current, we can assume that there is an inductor in series for smoothing processes, and that inductance L is affecting and creating a current, a DC current, okay? If you can use all the mathematics, but what I need that my students remember is that the current will be basically depend on alpha and gamma, depending of the cosine of alpha and alpha plus gamma. That is the direct current that you will get, okay? Depending on the commutation angle and the delay angle, that will define what is the current that you are allowed to produce using this power converter. However, the interesting thing here, I don't know if you realize, now we have equation for voltages, and now we have equation for currents. This is the equation for the current. Over here, we have a equation for the voltage, okay? What I want to show you now is that we can convert those equations, into an equivalent, a Thevenin equivalent model, okay? I don't know if you realize, but you can imagine the terminal DC voltage, VD, like the composition of 2 terms, okay? One term that is created by the voltage, the commutated voltage, V0 cosine of alpha. Okay, and the second voltage is the voltage drop across this device, and the voltage drop across that device, RCID, represent the voltage drop created by the commutation, but that is not a physical resistance, okay? We use a resistance over there just to show you or to represent or to simplify your understanding about the process. In real life, there is no resistance over there, but we are using that resistance in order that you can simplify the calculations, okay? Later in this presentation, I will do the same with the inverter, okay? We will create a similar model like that, and don't be surprised if we found a negative resistance, okay? In this case, it's just a voltage drop over there, but don't be surprised in the case of the inverter, okay? What I need that you understand also is that the power factor that is produced by the converter on the AC side is something that is quite interesting, okay? The power factor here, the power factor, you can imagine the power factor like the separation between the current and the voltage, okay? I will not go in full details over here, but what you need to understand is that you can understand the RMS value of the line current like a supercomposition of the several frequency signals, okay? What I'm telling you is that this current over here, it can be reconverted or can be converted using Fourier analysis, okay? And Fourier say that any periodic wave can be reproduced by the sum of sines or cosines, and that is what we are doing over there, okay? At the end, I need my students to understand over here that the cosine of phi depend of the cosine of alpha, and again the cosine of alpha plus gamma. What I'm telling you is the cosine of phi depend on the delay angle and the overlapping angle or commutation angle, okay? Now the situation start a bit more interesting, because right now we will discuss about the inverter operation, okay? The inversion operation is a bit different to the rectifier operation, okay? In the inverter operation, we have some DC signals, and we are taking that signals and converting into the AC system, okay? And over there in that figure, what I am showing over there is the waveform when we have an alpha angle over here that is 90 degree, okay? 90 degree, and that means that we have a direct voltage 0, and that is when we start to move from the transition from rectifier to inverter action. What I'm trying to tell you is if we have any bridge rectifier, and progressively we start to increase the delay alpha, the angle alpha, the output voltage start to decrease and becoming 0 when alpha is 90 degree. And basically that is the representation over there. However, if we still increasing the delay, the average direct voltage become negative, and then the applied direct voltage then start to force the current through the bulb again to the nominal, to the negative pole, and then back the voltage, okay? What I'm trying to say is an inverter bridge is basically a rectifier bridge where alpha start to be beyond 90 degrees, okay? Okay, over here I am showing you, and this is a inverter operation, and right now you can see over there the bridge, and in this bridge we have those in this bridge we have currents and we have voltages, okay? And okay, again, we have here the bridge, okay, and we have here some transformer going to the AC side, and we have the DC side over here, okay. Here they are here you can see the voltages, okay, the voltages across different section of the bridge, And in red color, you can see the current that is going through the commutation device, 1, 2, 3, 4, 5, 6. And finally here, downstairs, you can see the current that is going through this to the line A, okay? There are very few conclusions that I need that you understand, okay? Using the appropriate sequence of commutation, 135, 135 for the negative size, and 246, 246 on the negative size, we can create voltages that they are moving across these, they are forcing current through these inductance, and those currents that they are, all of them are positive across those commutation devices. They will create a positive and a negative currents moving through this transformer and creating the AC signal, okay? I can go here in details about the commutation between valve 3 and then there point B and point A, the valve 5 start to be conducting and is triggered, and then because we have a negative voltage over here across those devices, well, the conduction is stopped, but because we have an inductance, there are some current remaining and decreasing across the device, okay? What is interesting over here to tell you is the following. Something that you must understand is, for instance, alpha used to be in the rectifier, the angle, the delay angle, okay? But the delay angle for a rectifier is typically a number between 0 and 90 degrees. 0 when we are without any gate control, and 90 is the maximum value, and you can realize that that voltage starts to be 0, the output voltage, okay? However, when we start to use a rectifier, the angle tends to be above 90 degrees, and it's impractical that we use alpha for inverters. Instead of using alpha, what we define is basically beta, and beta is basically the delay angle, but in terms of an inverter, okay? Something that you must understand, from here to there, they are 180 degrees, and beta is, if for simple inspection, is 180 degree minus alpha, okay? Gamma is still the same angle that we use in the rectifier, and gamma is still the overlapping angle or the time delay, okay, for the commutation process. But right now we need to explain something that is very important, and that is the angle gamma, okay? What is the angle gamma? I believe all of you can see over here that from the stopping point of commutation, and because the voltage across the devices is negative, there is this small peak going over there until the conduction of the valve 3 start to conduct again. That alpha, that delta, this angle over here, this small angle over there, is what we call the extinction angle, okay? The extinction angle is basically the angle that that is the time that is allowed in order to the gate to regain control from the commutation process, okay? Is basically an angle that is coming from a time, and that time is the time that is required for the commutation device to regain control, and it in order to be switched again, okay? You must be aware that when we send a signal to the gate, the commutation process is not a 0 seconds. There is a small time difference between when the gate receives the signal and when they start to conduct. In some devices, the time is at the scales of microseconds. In other devices, could be a bit higher, okay? Okay, but what I need from this slide is that you understand that right now, when we are using the inverter operation, Now, when we are using an inverter operation, right now here we have the current that is going into the inverter, and here we have the voltage across the inverter. And right now, as you can see, the equation is still using cosines, but now we are using the cosine of the extinction angle and the cosine of beta. Beta, as I said before, is the new delay angle, and that is basically alpha 180 degrees minus alpha, okay? That is what you need to understand here. And well, if you remember, I told you that the main objective of us here is to create a simplified, useful equivalent model for the inverter and the rectifier, okay? For the rectifier, I introduce a model that is using a voltage in series with a resistance. I already clarified at the rectification section that resistance is not a physical resistance. It's basically a resistance that is used to represent the voltage drop created during the commutation process inside the converter, okay? Here, as you can see, we have an equivalent circuit of the inverter, but in this case, we are using the angle of advance, or the convert delay angle beta, and in this case, the resistance is positive. However, if you prefer to use, instead of using beta, you start to use delta, well, be careful, because this symbol over here must change, and right now when you are using beta, that number should be negative, okay? Please be careful, don't be scared with the negative sign over there, okay? What I need that all my students understand, that this is not a physical resistance. That is an equivalent voltage drop, and that equivalent voltage drop, we use that equivalent resistance, okay? And the negative sign is coming from the Kirchhoff voltage law that we obtained from the commutation, okay? Now let me combine the total direct current link, okay? Over there, I believe you can see the total equivalent, the complete equivalent circuit for a DC transmission link, okay? Over there, you can see that is the classical behavior in a steady state operation, okay? This model over here, this model that I am showing you, that model is only refer and only valid for a steady state. That means that those angles over here, you must realize that this is the rectifier side and this is the inverter side, and that is the reason that the current is coming from the rectifier to the inverter, okay? Here we have the resistance inside the DC link or the DC loop, okay? And what I need that you understand over here is that current is basically this voltage minus this voltage. VDR represent the voltage across the terminals of the rectifier, and VDI represent the voltage across the terminal of the inverter, okay? On the other hand, this is the resistance, the equivalent resistance of the model. Remember, that is not a physical and real resistance. It's a resistance coming from the voltage drop across the commutation during the commutation process. And this is the resistance on the inverter side coming again from the commutation process, okay? That means using those equations is extremely simple. If we know the terminal voltage between the rectifier and the inverter, we can obtain the current. And we can substitute here if we know the internal voltages inside. This is the voltage that is inside the inverter and the rectifier. We can obtain here using this equation In this case, this equation we are using here cosine of delta, and if we are using delta, you must remember that this resistance over here is negative, and that is the reason for the negative value over here at the denominator. Okay. If you have some doubts about this equation, please go and check a Wiley book, equation 9.17. Okay. Finally, okay, we close here the explanation about the DC link, and we have presented the most important equation for modeling the DC link. Okay. Now, what you need to understand is that the LCC or current source converters, they have a very important components around the converters. Okay, the converters, they are doing the heavy work, and that is the commutation. They are closing and open. We're closing the switches and I'll open them to open. Okay, and they are doing a fantastic job in terms of commutation. Okay, however, in reality, power electronics colleagues, they must recognize that there are many more controllers surrounding the converters. Okay, there are many other elements like, for instance, current transformer or current transducers looking into the current that is in the DC link. Okay, those signals will go into controllers in order to define if we need to modify the angle control, the extension angle control, or if we need to modify the current control settings. Okay, that is basically two control loops that you can identify over here. Both of them are going into the phase looked oscillator. As I say, those controllers, they are sending signals to the phase look oscillator, and then the closing signal or the signal to the switches, they are coming from the phase look oscillator. Okay, those controllers over here, they are quite fast, and they are basically ensuring the proper operation of the DC link by controlling the current acting on the extension angle. Okay. On the other hand, as you can see over here, they are transformer. This arrow over here represent the top changers. In this case, we have controllers representing the top changers. Okay, those controllers, they take in account the alpha and beta. They are coming from the commutation, from the converters controllers, and then the tap controller sends signals to change, increase or decrease the tap position in order to control the supply voltage or the receiving voltage on this DC link. Okay. This schematic diagram represents the most basic control system that you can find in a HVDC link based on current source converters. Okay, basically the rectifier and the inverter change role as required when the power flow dictates. Okay, however, it's required those kind of two layers control level, and that is basically the constant extension angle control and the constant current control angle. Okay, what I will show now in this figure over here, what I am presenting is basically the current voltage characteristic of the converters involved in a DC link when there is some compounding. Okay, over there what you can see is we have in red color, you can see in red color, this red color over here represent the characteristic, operation characteristic, voltage versus current for the converter station A. And on the other hand, in blue color, you can see over there that is the voltage current characteristic for the converter station B, okay? In this case, the curve starting from P going to Q, R, S, T, the curve P, Q, R, S, T represent the converter, the operation of the converter A, okay? Between the point P and the point Q, basically the converter is working as rectifier, and at that case, that is the optimal characteristic for a minimum angle alpha, and that minimum angle alpha is known, okay? That is basically the rectifier operation, okay? However, when we reach Q, as you can see over there, as the current rated of the bulb, the current limit of the bulbs cannot be exceeded, okay? And if we are working a constant current, then, well, the control will be working in this region over here, that region between Q and R, that represent the operation at constant current. You can see that is the reason that we have this vertical line. That is the operation at constant current. And in that case, the angle alpha is increased versus the voltage that we are obtaining, okay? This is the operation at constant current, but the voltage could be in this area, okay? Basically, the idea is that in this operation, the current is kept constant, but the voltage across the DC link is allowed to fluctuate, okay? But now the output voltage current characteristic reach here the point 0, and that is the point R, okay? And that is when the converter now start to work as inverter, okay? In this region over here, in this region for the voltage, positive voltage, we are talking about this was the rectifier operation, and now because the current is going down, and this is a constant current operation, at this constant current operation, the station A behave like a inverter, okay? Between R and S, that is the constant current operation, and then from S to T, that is basically when the converter start to work it at a constant station angle, and in that case we will say this is delta 0, and during that regime we allow here this value to be constant, and because the current will be changing, well, the voltage across the inverter will change. It will be reduced by this amount, and between S and T we are operating at a constant excitation angle delta, and that is basically when we cover all the operating modes of these converters, okay? The history is similar to the another converter. In this area is working as inverter. Then here we have the current constant operation mode, and then we have here now constant delta control, and that is for the case of rectifier, okay? Okay, now let's move on. And now what I am showing here is the inverter and rectifier operation characteristic. In this case, when we have a constant current component, and basically when we have two operating conditions between two different converter stations, the intersecting points, they represent the operating characteristic, the operating characteristic of the device, okay? What I'm trying to tell you is that in this case we have the rectifier and we have the inverter, and we have those characteristics, and when they intersect each other, the voltage and current characteristic of the first quadrant of one of converters. One of them must be rectifier and the other one must be inverter. If converter A is operating as rectifier, converter B must be operating as inverter, okay? And in this case, when we have the intersection of those characteristics, for instance, the current constant current control, then we have the characteristic of the whole system expressed in terms of the current, okay? Under normal operation, the inverter operated at constant extinction angle control, and then the rectifier is working at current constant, okay? And this is something that is something to understand, that both converter stations, one must be inverter, the other one must be rectifier, and they must have different operating controllers mode in order to allow the proper operation, okay? Well, it's time to talk about the HVDC transmission systems, the LCC. And right now, what I will talk about is the possible configuration, possible arrangement of conductors when we are using DC transmission, okay? As you can see on the top, I have the ground return, because you can see here this is the conductor, this is the low resistant conductor, and we have here the grounding, and we are using ground as return of these currents, okay? Another alternative, I already told you, that is the case that we are using a metallic return, and in this case the return can be used a metallic, a low quality metallic conductor, or it could be also high quality cable to produce the return, okay? And finally over here we have the bridge arrangement. The bridge arrangement is basically when we have two bridge in series, as you can see over here, and in the middle point or the top point we have the connection to the grounding system, okay? That is basically the bridge arrangement. This is used typically when we have a few conditions, okay? First, the grounding return in normal operation typically has current zero, but if one of those converter station is out the service, we can keep the service using the return in this loop over here, okay? Also, some HVDC systems, they are built in stages, and it's typical that you install first the first pole over here with the ground as return, and then in the second stage you install the second set of bridges and the cable, and then you have a bridge arrangement with two bridges at each converter station, okay? Well, I don't want to talk bad about this, okay? I'm not a power quality person. I know about power quality, but there are few of my colleagues, many of my colleagues, that they are expert on power quality, okay? Power quality is a very interesting topic, and one of the sub areas of power quality is related to harmonics, okay? You must be aware that when we have some commutation devices like the thyristors, because the way that they behave, chopping or cutting the voltages and currents, well, those cuts that create some distortion in the signals, and we can use harmonics to represent that, okay? What I need that you understand is when we are using thyristors, especially thyristors, there are some harmonic components of voltages and currents inside the power system, okay? And what we need to be careful is that those harmonics, they have effects in many different components. The effects are very different, but there are some negative effects, okay? There is possibility of resonance. That is something that everyone knows. For instance, if you are having some capacitance in the systems, you must be careful because those resonance can destroy those guys, okay? And also, if you have communication circuits nearby, those harmonics are high frequency, they can create interference, and we need to be careful about this enhanced interference with the communication system, okay? What I need to understand is that the output, direct voltage output of the converters, the waveform contains some harmonics, okay? And those harmonics results in current and voltage harmonics across the line, okay? They can be reduced by adding the inductance that I already showed you in the previous slides. That receives the name smoothing or smooth inductor, okay? The inductor is trying to flat this ripple at the current and those harmonics, okay? And also the converter currents at the AC side, also they have some contains of harmonics, okay? However, we try to use some physical tricks like using the connection of the transformers that we use to supply the bridge converters in order to minimize those harmonic components. If you were a bit careful, in the previous slides I show you the transformer connection as a delta star connection, okay? Delta star transformers, they are typically used in the supply for those bridge converters, and one of the idea is to reduce the harmonics, okay? And however, that is not that is helping, but it's not the full solution, okay? Over there on the right hand side, you can see a very interesting plot. And that plot is basically the variation of the seventh harmonics currents in terms of the delay angle alpha and the commutation angle beta, okay? As you can see on the horizontal angle, you can see gamma over there, that is the angle of overlap. And in each one of those lines over here, you can see the different plot for each delay angle alpha, okay? Starting from alpha 10, going into alpha equal 80 degrees, okay? That variation of the seventh harmonic component is basically related with the commutation or overlap angle and the delay angle, okay? Typically, those harmonics are reduced by decreasing the angle alpha or the overlapping angle, but this can also produce some other harmonics in other places, okay? When you are working with converters and you try to modify one of the parameters, you are affecting somewhere else, okay? Changes in alpha, a given value of gamma, do not imply large decrease in harmonic components, okay? However, what you need to understand is that those harmonic voltage and currents, they are produced in the AC system by the converter's current waveforms, okay? And they can propagate into the AC systems, and that can create problem. That is the reason that typically at the converter stations, there are a very big set of filters on the AC side, okay? Typically, they are using LC filters, what we call resonance LC shunt filters, okay? And they are typically tuned in order to reduce a very specific harmonics, okay? Over here, you can see this is the single line diagram. This is the single line diagram of the main circuit of an HVDC system. Of course, this is based on thyristors. This is a LCC system. And in this case, this is This is including filter banks and shunt compensation, okay? As you can see over there are some shunt filters, LC filters, and you can see several MVR connected at the AC side. You can see over here some filters, and those filters are basically in order to reduce harmonic frequencies, okay? Very specific harmonic frequencies, okay? As you can see, the complexity of a HVDC, LCC, or current source converter installation is not only coming from the converters. The converters, if you are using thyristors, they are extremely robust and very simple. However, the controllers and all the filters, paraphernalia used around, that is what is complicating the situation, okay? And that is the reason that we start to use something that we call the voltage source converters. The voltage source converters, they are quite useful, they are quite important, because in those voltage source converters we can use some switching devices that we have the control when we close on and when we close off, when we open those devices, okay? I believe over here you can see we are using the classical transistor over there, and in those transistors what we are doing is switching on and switching off, okay? We are using those devices and as commutation devices, okay? What is on the right hand side? On the right hand side, what you can see over there is the voltages across different sections of that system, okay? What you can see over there is the voltage across different sections, and in this case, as we are using a totally control for the on-off action, we have full control about the average value of that signal over there, okay? And in this case, we can use IGBT in order to switch on and switch off rather than thyristors. Thyristors, they don't have the possibility of controlling the switch off. Sorry. Okay. Voltage source converters over there, you can see a typical configuration, and this is a three-phase configuration. And in this figure over there, you can see a full bridge of a voltage source converter. In this case, we are using basically a transformer, and that transformer coming from the line ABC is providing the connection to the full bridge, the three-phase bridge of those commutation device. Okay. Now the interesting thing here is that using those gates over there for each one of those switching devices, using a very specific way, how do they close and open, well, we can create a better signal, okay, compared with the LCC. Well, I already talked about the pulse width modulation, PWM, okay? What is the PWM? The PWM is basically a technique in order to define how the switches close and open, okay? As the IGBT can be switched many times per cycle, during one cycle of the AC signal, then we can use different ways in order to close and open those switches, and we have full control over closing and open, and we can do that many times per cycle, okay? One of those techniques is the PWM, okay? I will not go in full details about the PWM, but what you can see over here is in blue color, we have the signal that we want to reproduce. That is the fundamental AC signal from a sine wave, okay? And in green color, we have this beautiful PW waveform, okay? The PW waveform for this half a cycle, as you can see over here on the top, we have a triangular signal in red color. And the PWM technique based on sine triangular pulse modulation is basically comparing the value of this fundamental signal with this signal in red color that we call the modulating signal. Okay, as you can see over here, there is an intersection with the red, between the blue and the red, and you can see here downstairs that is a negative value. Okay, then from here, from this intersection to the next one, we have a full positive rectangle over there, and then we have another semi-cycle going to negative. What I'm trying to say is basically the sine triangular pulse width modulation, PWM, is basically comparing this modulating signal with something that we call the carrier signal, and that is basically a reproduction of the fundamental frequency. Okay, and as you can see over there, we will have a signal that is basically between two extreme values, and what we have here is empty spaces that they depend of the comparison between the modulating and the carrier signal. Okay, that is one of the best approaches in order to create a switching sequence for the IGBT inside a voltage source converter. Okay, something that you must be aware is those techniques now can be used for switching more and more switching devices. Okay, in reality, for high power applications such as HVDC, we need to have many of those IGBT. Remember, the IGBT has an issue because they don't have so much voltage and current values compared with the traditional thyristors, and that is the reason that we start to use many switches in series and parallel. Okay, and one of the solutions to increase the voltage is having many switches in series. Okay, over here we have many switches in series. We have 2, 4, 6, 8 switches, and in this case we are creating a basic three level modular converter. Okay, in this case we have 3 different voltage levels and we are using 8 switch device. Okay, however, if we increase the number of switches and we increase the number of modules of those switches, well, right now we can start to increase the quality of the converter signal. Okay, increasing the number of switching and using an appropriate switching sequence, we can obtain a better signal and something that resembles better a sine wave. Okay, and for instance, in this case we have here the 5-level modular converter, and it's possible that using appropriate sequence, the PWM generating the switching signals, in order that this 5-level modular converter create a signal that behave similar to what is a classical AC signal. The theory say that if we increase more and more the number of switches, of course we will resemble more and more closer to a sine wave. Okay, now we are almost at the very end of this session, and what I will do now is I will discuss a bit about the control of voltage source converters. Okay, one of the things that you must understand is the voltage source converter has so much controllability compared with the CSC, the current source converter. The voltage source converter, as this device behaves like a voltage source, allow the behavior that is similar to the behavior of a voltage source in series with an impedance. Okay, what I am telling you is that those voltage source converters, they have a DC side over here, and we are using this one as inverter. And when you are working as inverter, you are delivering current to the AC system. We are delivering a current I, but also you are delivering P and Q, active power and reactive power. Okay, And over there, you will find the beautiful equation for the active and reactive power. I don't need to run any demonstration on those equations because all my students must remember those equations over there. Those equations for P that represent the power angle equation, that is a very famous equation that has been used for the classical model of the synchronous generator, but also it's used for the power transmission at transmission lines, okay? And the reactive power is also another very famous equation. What you can see over here is something quite important, okay? The maximum power that you can deliver by a converter depends basically in three important things. One is the internal voltage that you can create, and that is the voltage across the converter. The other one is the reactance that you have between the converter and the system where you are connecting for. And the other thing is the internal angle of the voltage at your converter, okay? Of course, the terminal voltage, it has importance for the power transmission, but typically we don't have control over there. In terms of controllability from the converter point of view, VSC, this voltage here is controllable, this angle is controllable, and the reactance is not typically controllable, okay? Okay, in the next slide, I will show you, okay? And this is a more detailed representation of the different controllers that you can find for a voltage source converters, okay? The first thing that you must realize over here is that instead of sensing current, we are sensing voltages because we are working in voltage source converters. And those voltage sensors, they are sending signals to the voltage control, and those voltage controllers, they are interacting with the inner current control, limiting the currents that they can go through the switches. Then there is something creating the PWM signal, and then those signals, they are sent into the bridges, into the commutation devices in order to implement the commutation and the sine wave or the rectified wave, okay? As you can see over here, the closed inner controller, the current loops, they are extremely fast. We are talking about a microsecond scale of the time constant of those controllers, okay? But then we can have reactive power controllers, then we can have AC voltage control, then we can have active power control, and all those controllers, they receive the name outer controllers, okay? And they are slower controllers. They can be in the scales between microseconds to milliseconds, okay? And here, I don't want to go so much detail, but basically they are more and more detail related with the voltage source converter control implementation. Something that you must be aware is that the voltage source converters, they are controlled using the DQ frame, okay? The DQ frame is similar to the DQ axis that we use for the synchronous machine. The DQ axis is the way that we control typically the voltage source converter, and over there what I am showing you is the basic representation of those controllers using the DQ axis, okay? I hope that if you want to know more about those controllers, you can read some of my papers. I already published some papers related with HVDC voltage source converters, and I have worked especially on the active power controller, on the reactive power controller, and the frequency controller that is not represented over there, okay? Until a few years ago, the HVDC systems, they were basically something passive in terms of frequency control, but recent research has identified the potential of using those voltage source converters to help on the frequency support of the power system. and I published a few papers in 2008, 2011, 2012 about this topic, okay? Well, today the summary is very simple. I introduced the main concept related with direct current transmission system. Then we spent some time talking about converters based on current source converters. Basically, we talk about rectification process and the inverter process, and we create some equivalent circuit for the inverter and for the rectifier converters, okay? And then we talk, we assess, we read some discussion about the performance assessment of those devices. And finally, I run some explanation about the voltage source converter, the VSC, and the active and reactive power control, okay? Finally, here there are some references. All the equations that I use for this specific presentation, it's been taken from the WIDI book, chapter number 9, direct current transmission system. If you have any doubt about any of those equations, please go to WIDI and read that beautiful book, and you will find many of the equations or all the equations that I use over there, okay? It's been a pleasure having you here in this video. Thank you for watching my videos about power system analysis, especially this introduction of direct current, okay? Thank you very much, and keep tuned on my YouTube channel. Thank you very much. Bye now.